immediately. Okay, so as I mentioned, no, let me just repeat that. No, you won't need to write any like final paper or anything like that for this class. It's the decision we have made, so you can be a bit more relaxed. Okay, as I announced last week when we had these lectures, today I would like to discuss some real life examples of data collection, and so won't give you some examples or let you share some examples. Now I know that in general, not many people, like sharing in this sort of environments, and you may not be comfortable with that. But in case someone here has like an example of data sharing, data collection that they have done, or maybe something that they will need to do in the future and they want to discuss it, I will invite you now to just raise your hand or write in chat or whatever works the best for you. I will give you like 30 seconds or something. Okay, so it seems to me that no one is writing, no one is preparing anything, so that's fine. So instead of that, I will go over. I have prepared a few of the papers I have published with my co-workers here, colleagues. Let me repeat, my name is Sandy Baresi Shegota. Professor Tsar is also part of this class. He helped me prepare the materials and so on. So I have selected some of different papers that we published over the years together that we can essentially illustrate you different. All the papers in question have different methodologies when it comes to the data that they used. All of the papers in question are machine learning papers. They all focus on different aspects of machine learning and modeling. So I will, but using data from different sources. So I will slowly, I'll go paper by paper. So I have 1, 2, 3, 4, 5, 6, 7, 8 papers prepared here, and I will just present some different approaches that we used. As we are talking, I'm going to post the links to these papers in the chat, so you can check them, download them. Feel free to use them as a reference if you ever needed them in the future or something like that. So yeah, if anyone has any questions, feel free to just turn on your microphone and ask, or raise a hand if you're more comfortable with that. Write in chat, and if anyone changes their mind at any point, feel free to share some example of data collection that you may have. So I posted the first paper in the chat. And we'll talk. So this was published back during COVID in May 2020, and the title of the paper is Modeling the Spread of COVID-19 Infection Using a Multilayer Perceptron. I think you may have mentioned what multilayer perceptron is in different in some other classes. Basically, it's an artificial neural network that works by optimizing the, let me see, maybe I have an illustration somewhere. I actually don't here, but it basically it adjusts the weight between the neurons to try to regress certain values. So why did I pick this? This is an example of data collected by someone else. So we didn't collect the data that we used in this study. It was collected by Johns Hopkins University, right? It was a pretty popular, at least back in the day when we were doing this, when COVID started. It was a very popular data set, and that's a pretty common practice that we have in research, especially ML research. Some people will just collect the data set and publish it, or do some starting analysis. and then publish that data online, right? And then people will go on to actually use that data for further analysis. What is necessary, when you're doing this first, picking trustworthy data is super important. You want to pick the data that is well collected, well analyzed from a source that you trust. That's the first important key when you're using someone else's data. You want to make sure that data is fine. So don't download it from like a random repository. Make sure it's published by like a university or a research group or something like that. The other, whenever you're doing a research that's based on someone else's data points and data research, one of the key elements is to properly cite the data set, the data that you're using. So, for example, here we can see that we have cited this data set, Johns Hopkins CSSE, with the link to it. So depending on the data set, so everyone can actually check the data that we used. We have given credit to the people that have collected the data. That's very important, and we can actually see if there were any updates or anything regarding the data. So we have a live link to the data. As you can see that, for example, this data set has in March of 2023 stopped collecting the sources. They are recommending some other sources, right? There are some other, I don't know if this still works, but there were dashboards that were provided for tracking the data and so on by them. If you remember, if some of you were in a big data class, I mentioned the dashboards as very useful things. Another thing is that basically you can see here we cited directly. Some data sets will have citation requirements. They will tell you, hey, please cite this paper or something where we describe why didn't we cite it here, why did we cite directly instead of this paper they are requesting, because we actually published this paper before they have published this paper, so it wasn't available yet for us to cite, so we cited it directly. In some later research that we had, we actually cited this article that they have published with their web-based dashboard. In the start, when we started doing this, if you remember, COVID-19 first cases happened in December of 2019. This was published relatively soon. You have to take into account that the publication process usually takes a couple of months, 1 to 3 months, for example. It can be much longer, it can be years in some cases. This data, that we used was available just as pure numerical data, right? It wasn't available as a dashboard, so that's why we haven't cited here, just as an example. But usually, if you are using someone else's research, basing your research on the data they collected and so on, it's very polite. It's actually, a requirement to find how they want it to be cited and cite that. If they don't mention a direct requirement, you can cite other places. You can cite the dataset directly, as we did here. Okay, so what are some other things that you want to pay attention to? When you're getting the dataset, as I said, you want to pay attention to the source, but you also want to run basic analysis, show how it looks like, how the data appears, so you can make sure it is published. The published data makes sense. Essentially, you want to check it, make sure there aren't any egregious errors through plotting the data and analyzing the data, seeing how it works. So that's example of public data sets. Again, it's very, very common to use public data sets. Why? Because people who collect the data may not have the actual, the actual tools, the actual capabilities for analyzing the data. Maybe they aren't familiar with certain methods that you are. So even if they publish the research, you can build upon that research. It's not in science. It's not considered like problematic or something like that. I know that some people who are scientists, I've gotten comments in the past like, "Oh, won't they mind that you have actually like used different method and gotten better results than them?" No, that's the point. You want to build upon their research as you move forward. Okay, so let me go with a different data set now, the different paper that we discussed. So this is something that was, this is an example of a data set. Well, as I said, for everyone, I will post the link so you can read it and analyze it. That is probably the best example of how you can collect the data set, and that is collection by, it was collected by Professor Mezek here, directly at the source of the data. This data set deals with the measurements, so mass flow rate, temperature and pressure measurements in different points in different points on this marine steam turbine. This was measured directly on the ship, right? That the measurement was done at a commercial LNG carrier. The data was collected directly there by someone who is very, very experienced in data collection. Not only data collection, but also the operation of this type of vessel, right? So the person who collected the data for us is in charge of operating all the machinery on that massive LNG carrier. And this is the marine steam turbine that's used for propulsion. Why is that the best example? First, we have someone who knows this by heart. It's their job, for multiple months after the year, 24/7. They are in charge of this propulsion system, so they know it by heart. They know how it works. They know which operating procedures are common, which aren't common, which needs to be included to properly model something, which don't need to be included to properly model something. So the data, even though they aren't maybe analyzing it statistically, they understand that the data, that they provide us was collected during the actual operation of something, right? And it was collected properly, so the values in the data set, they were actually, written down, right, copied from the operation, from the dashboard they use for monitoring these elements. So as they were noted down, as they were collected, they were immediately checked, right, without by the person collecting them. So we know that all the values are real, all the values are correct, realistic, right? The other benefit of collecting real data from the real source, we will talk about simulation data collection later on, but the main benefit of this is that you're collecting noisy data that will include possible information, possible expansion, possible, shapes of data that aren't necessarily available in 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 a simulation environment. Because why? Because, well, maybe there is this shaft for the propeller one, in some sort of a simulation, it will be, it's an ideal shaft. In reality, maybe it's a bit unbalanced, and that influences something. So you can actually model this steam turbine set with the high pressure, low pressure cylinders, and so on. You can combine it, you get the real data that may be influenced by some imperfections in the actual data set, and you show that you can actually model that data, right? That you can actually illustrate it, because if you have perfect data, you can think of it, if you are, what's easier to model if you are trying to model something like like a, if you have an X and Y axis, and now you're trying to model, a mostly straight line, or you are trying to model a more realistic line that's, has some noise. Obviously, it's much easier to model that line that is mostly straight, that doesn't have noise, but realistically, most real data that you collect is going to have some noise introduced to it. And if you can model that, that's much more complex, and it shows a wider validity of your data, right? Of your models, they can actually be collected together, that they can actually be applied in the real environment, because, well, would you trust, the data that was modeled on a simulation? Would you trust it for the application because it doesn't include these sort of noises, imbalances, and stuff like that can happen? Just a second. I apologize. There was someone at my door. So that's one of the examples, that where you want to use real data to actually model stuff if possible. We'll discuss some cases where that's not possible. Something that you want to apply here when you're. So what's the possible problem with real data? Well, the possible problem with real data is that you can collect a lot of it, right? This was collected. As I said, this is an actual. We have a picture of it because I don't think they would like, the actual photos being published. But this is, a real operating propulsion system on a vessel, right? So you can't just play around with it and set it up. There are certain realistic configurations that this model can be set in, right? And you can have tens of thousands of different data points because they are either unrealistic or they won't be actually used, right? So they aren't realistic as an actual data point that would happen. So what happens here is, well, we only had something like 200 data points or something like that. I don't remember exactly, and we have a problem that's called, we have a small data set. So when we have a small data set, what is the problem? Well, we are essentially running into a problem that's called, that we can easily overfit it, where if we have, this is our data set, and we are just going to, so this is our data set, right? And out of this data set, we are going to be using this part for training because we need to use, I don't know, 90% of the data for training. And we are only validating on these 10 data points here, right? Now, these 10 data points by themselves, these 10% of data points aren't necessarily a problem if you're talking about 20,000 data points in total, because now suddenly this is 2,000 data points. But when we are talking about 100 data points, these 10 data points are now these 10 data points are now just 10 data. This 10% of data points is just 10 data points, and you can just get lucky. You can just get lucky with a model that's guessing these 10 data points well. So how can you, avoid that? How do you make sure that this isn't the case? Is you run something that's called k-fold variation. I don't know if you mentioned it in some other classes. I'm just going to briefly talk over it. So you take your data set, you split it in a certain number of parts. In this illustration, it's 5 parts. And then you train 5 different models. The same number of parts you have, you train 5 different models. In this model or here, you will use the first part of the data set, first of the 5 parts of the data set for validation to calculate your score on and train it with these 4, right, remaining ones. Then the other model, you will use a different part of data for evaluating it, and so on. Third, fourth, and fifth part of data, you get 5 models which were trained on a different parts of your data and validated on a different part of your data. Why is this nice? Why is this useful? Because you essentially tested your model on each part of your data set. So you tested your model across all the possible values that were contained in the data set. That's super useful here because we have a small data set and no one can complain to us, tell us like, oh, you just got lucky, you got this part right. You have with this, we know that our model, whatever it was, whatever we formed it as, was trained on all of the data in it, was validated on all of the data in it, and we can express that. We usually express it as a mean value and standard deviation. If all of the values are above 0.99 right accuracy, we can call that like, hey, we have a model that would work on all possible data permutations. So that's something that again, you have realistically collected data. There is always a trade-off. Ideally, your data set will be collected in real environment and have a lot of data points, but it's not always the case, and you need to adjust it in some way through your methods, because sometimes you just can't collect more data points, right? Those are the operating regimes of this marine steam turbine. We can make up additional regimes, or we can like make them up mathematically. If we say like, oh, the pressure here is this much and this much, yes, we can do that, but realistically, that's not a value that it's even possible to be set in actual operation of the turbine. So that's something that we possibly want to avoid. So let's talk now about, I mentioned, you have realistically collected data. What happens when you have realistically collected data? But now we're talking about images. And we're going to talk about something that's called data augmentation here. So what is data augmentation? Well, again, when you collect data like this, these are the different classes. We have people who had mild clinical picture. All of these were people who were diseased with COVID. Some of them had a mild clinical picture. You can see that the lungs are pretty clear. Some they had the moderate, severe, or critical. Those are the classes that we had, and we were building a system. This was data that was collected across multiple hospitals in Serbia and multiple hospitals in Croatia. We were trying to build a system that will basically be an expert support system and tell them like, hey, this is, this person doesn't have that hard of a case. Maybe they can be sent home, or they don't need to be watched as closely. This person has a critical case. We need to send them immediately, to maybe get an inhalator or something like that. Because to lower the impact on the healthcare system that was very big during COVID, right? So here are the numbers of what was actually collected. You can see that we have 38 plus 30 plus 34 plus 83 data points. We have around 200, less than 200 data points in total. That's not an ideal situation. You have 200 images in total. Ideally, you want to have over 1,000 images. Now, you don't want to wait. You have to do what you can. In some cases, it's simply not possible to collect more data, or it will take a long time. So one of the things that you can do is data augmentation. There are two types of data augmentation. In this paper, right, we are going to use something that's called geometrical or deterministic augmentations. What does that mean? It means that we are applying a certain transformation, such as this 90-degree rotation around sagittal axis. This simply means that if we input the same picture, we use this operation, the output is always going to be the same. That means deterministic. So you can see that we have a 100-degree rotation or a flip. Combined, we have different transformations here. In addition to that, on each of these, a different factor of multiplication, so for each pixel was used, that essentially accomplishes here I actually found a mistake. So that's 0.8. This should be 0.9. This is 1.1, 1.2. What this actually does is it darkens or lightens the picture. I don't know if we have an example. No, we don't. So what happens now? Well, now we have a much bigger. So we have done for each of those images, we have transformed them, right? We have transformed them and we have applied this lightening and darkening using this factor by multiplying the images, and we get a ton more images. Now we have a few thousand, we have like almost I think it was over 5,000 images all together. So we have significantly increased the amount of data in the dataset from what did we say? It was 185 before. We have increased it. We have provided more data to the training set. We have now increased it to, let me just add this up quickly, to 5,400 or something like that. So how are we going to split that? Well, we're going to split that into training set, right, that we're going to use, validation set we're going to use, and you will note that we have a testing set. What is the testing set? The testing set, and this is very, very important. This is a classical mistake that I see in papers that review. Students do it if you're doing augmentation, right? It's not completely different data points. This and this are still the same person's lungs, right? You haven't added anything critical to it, any critical information. You have just represented the same information in a different way. So if you train on this image and you try to classify this image, which is just a bit lighter than this, you will get extremely good results. So when you're splitting your data for training, this test data, these 35 data points, they haven't been amplified. They haven't been augmented. These 35 images weren't included in this multiplication. They haven't had this process applied to them. They are completely unseen by the data. This is very, very, very important. Whenever you're doing any sort of augmentation, any sort of data generation like this, you want to have different. You want to have the test set that you use to determine the actual scores of how well your model performs. You want to evaluate it on separate data that wasn't used to generate additional points. Okay, so please remember that. If you forget everything else, please remember that. Okay, so I talked about deterministic augmentations, where I said, like, when you put this picture, you will always get this. Well, there's nothing random about it, but this again isn't great because the amount of information that you introduce, we are doing this to introduce additional information to the dataset, so our models can learn more easily. But we could introduce more information if they weren't deterministic, if they weren't easily, pointed towards the same fact. So here is an example of that type of data augmentation, which uses something called generative adversarial networks. So what are generative adversarial networks? Well, let me just find an image. So let me present what was done in this paper. In here you have cystoscopy images of healthy urinary bladder, right? So urinary bladder tissue. You have carcinoma in 3 grades: in situ, low grade, and high grade, right? These are the examples of the images in there. So what is this GAN? What is GAN? How does it work? Well, there's actually a better illustration here. So what you do is you train one neural network. That neural network is going to be capable of distinguishing between real data that you collected and random data that isn't this, right? Any other picture, right? It's usually like a random noise, but you can use randomly collected images or anything like that. You train this network to classify whether it's a real image or not a real image. Okay, that's simple. Then what you do is once you achieve a good enough score in training this, you train something that's called a generator network. This generator network will take a random noise and through application of different filters, that's convolutional networks. I don't know if you mentioned them in other classes. It's just a type of a neural network. This type of networks are going to generate information, right? So instead of classification, we are just taking this random vector of like 100 random values, and we are expanding it into an image, right? Once we do that, we feed that into this discriminator network that we trained before, and it's going to tell us, no, this image is false. Okay, take that back, retrain this generator, and keep retraining that until we manage to essentially until we manage to break the discriminator break it to get it to misinterpret the image. And once we manage to feed to falsify the data here, once our discriminator thinks that the data we have generated is real, we repeat the process, but we now retrain the discriminator with the data that we got here, and we train it again to differentiate between this initial data that we used here for generation, right? That's it with this originally collected actual data, and we train it to discriminate here. Then we train the generator again, trying to essentially falsify the data against the discriminator. We are repeating that process one after the other, hoping that we will get the images that are good enough that this discriminator can't differentiate between them, like our generated images, and this data. How do these images look? This is the training after 100. 250, 500, and 1000 epochs of training. So each epoch of training is that one of those iterations of feeding all the data here and repeating it. So it's a very lengthy process. And you get images like this. You will see that this image here has a certain effect, a certain artifact. That is something that we notice as people when we're looking at it, but the neural network actually won't notice this data because of the nature of how convolutional neural networks work, how the data is filtered, and so on. So that's the difference here. But you can actually, so that's something that you can use, and because you're using this, so if you're generating data we set like DALL-E for targeting, we're targeting people, right? You obviously wouldn't be satisfied with something like this, but because we're just using this data to train neural networks and to artificially increase the number of data points that we have, well, it's perfectly fine for us because this is going back into the neural network. Again, we also use this folding. We use different architectures. Basically, what happens is that when you are using the data, right, that you this newly trained GAN data, you have a slight improvements in scores compared to not using it, right? And you can artificially increase the amounts of data in a much better way than just flipping the image because you're actually generating new data. So that's something that's called synthetic data. This is a synthetic image data, right? There are some other examples. Yes, let me just get I have closed this. Let me find it. So another example is, for example, here. I apologize. It's asking me to confirm that I'm not a robot. So as I'm not a robot, for example, you can use that sort of data to expand information. For example, this research was initially, this doesn't have any synthetic or newly generated data or anything like that. It's something that one of our colleagues, Darren Meinarich, he has collected the information on ships, container ship shapes from various databases. The problem with this is that this is a relatively small data set. And why is this data set relatively small? So it has a total of 250 container ships. Well, because once you build a ship, you copy it, right? You don't design a new ship each time. Once you're happy with how the ship looks like, you will make 20 of it before you move on. So there is a limited amount of ship forms that of this size that exist, right? That are used, that are actually used today. So there's a limit of real data that you can actually use here, and that you can actually use in the use to develop models and train them and so on. And that means that you can't improve your scores beyond this. You can, because you are limited with the amount of data. So after we did this, we got decent scores, but we weren't completely happy with them. This was a proof of concept. The follow-up research here. Sorry, let me just copy it for you. The follow-up research here was, that's wrong research. I apologize. I used synthetic data a lot. Let me just find the actual. Here, yes, here it is. My apologies. So here is the improvement of these container ships main particulars. Main particulars simply mean the main measurements of the ship, like how long it is, how wide it is, how deep it is, and so on. So what happens here? Let me see if I can find the example. This ship here, it doesn't exist. It was generated synthetically based on the data that was collected, the data that existed, right, from those 250 ships which actually exist out in the world. We collected the data, we generated this synthetic form. So this is a vessel that could work, could be mounted, could be used, could be built, but it doesn't exist. It's just a produce of generative artificial intelligence. This was, much more impressive before, DALL-E and ChatGPT and stuff like that. This predates it a bit. Basically, what we used here is, our real data is these purple points here, and we use certain statistical methods that are called synthetic data generators, such as triplet value autoencoders or copula GANs or CityGANs. They're similar to that. They're all similar to those GANs that I described previously, generative adversarial networks. You can use them to generate data that actually, as you can see, has certain similarities to the existing data. You're essentially filling out the gaps in data that don't exist, right? So each of these points, right, across these graphs, all these points across these graphs are possible data values. So what are these? Are possible data values? Okay. So this is an example of how we can actually improve data in cases where we can't actually collect more data simply because it doesn't exist, and that's something that's very popular. I have another example of how you can generate synthetic data. So when we're talking about synthetic data, here is another example here where we use. So this is called utilization of multi-layer perceptor for determining inverse kinematics of industrial robot manipulator. So when we are talking about a robotic manipulator, this is a robot, right? An industrial robot. Direct kinematics are telling us if I move this joint here, if I move this joint here, basically if I know the positions of individual joints, how can I, what is going to be my position of the end of my robot, right? So if I want to position the robot in space, I have to move this joint, there are 6 joints total here. You can see each of the axes noted, and I need to put them in a certain position to be able to actually, move this robot. Now, calculating direct or forward kinematics, where I put like this in certain position, this in certain position, and calculating in the top is pretty simple. Doing the inverse is much more complicated. And so inverse kinematics mean that, hey, if I want to position this robot in XYZ position, right, I want to place it here, the top of it, because here is something I want to do. It requires a quite complex mathematical procedure. So what we did here is we generate synthetic data from mathematical simulation. What did we do? We calculated this forward kinematics, right? And we generated a data set. Let me see if I can. So this is the process of generating those kinematics. And basically what we do, these are the equations that you get and so on. This is the simple part of the equations. The others, are the ones for calculating stuff backwards is much more complex. So how are you? So what did we do here? Well, we said we have these joints, these inputs, 1, 2, 3, 4, 5, 6, right? And we have the positions X, Y, Z. When we do the forward calculations, we are inputting these values and getting that X, Y, Z. Now, instead of that, we're just going to flip this on our head. We're going to use X, Y, Z as input and this as outputs. What is the benefit of this? It's this data, neural networks, once you train them, are much, much faster compared to determining this mathematically, right? It takes a bit to train them, but they are much, much faster to actually determine the information. So what did we do? You can say that we have a very, percentage-wise, we have extremely low errors here. All of them are way below 1%. This is the highest at 0.5%, right? We get 6 models and we can easily calculate that. So this is the data that wasn't collected anywhere. It's just pure mathematics, right? We are just we could get the same solution with just mathematical equations, but we are just trying to collect the data that's simpler, right? And this data is actually, if you ever need it or something, this data is actually available online. I'm going to share the Kaggle repository that you can use for calculating the data, backwards if you need it for a project or something. You need a data set. Feel free to use this one. So that's an example of using purely mathematical data. Here is another. So we have something that's called dynamics modeling. When we talk about I talked about kinematics modeling of the robot. That's where it's placed. Dynamics are telling us what power we need in each of these joints to actually move the robot. Now, why is this problematic? Well, the equations for this robot that I've showed you here, it is. This is my little pet that I have in my laboratory. It's ABB IRB 120, right? This robot is equations for each joint, right? To calculate the actual full energy that you need to use without simplifications and so on. Because you can just simplify and assume that this is a tube, right, and so on. But actual equations that are used, precise equations that are used to calculate it, are around 50 pages long. 50 A4 pages. I actually have those equations in my thesis, my master thesis. That was calculating. That was my work. Let me see if I actually have them here, or if I might have them somewhere. No, I don't think so. But basically, they are very, very complex. They are okay. I have one. Let me just open it and show it to you. Essentially, this is the equation for the first joint, right? This is what it looks like. It's the whole file is around 15 megabytes, right? With just sines and cosines and speeds and positions and accelerations and so on. It's quite an equation. The problem with this is that it's slow. If you try to run calculations, loading this into memory, calculating it, it's very, very slow. So what we did, we know that these equations are correct. And using these equations here, like as I showed you, we can actually generate the data set. As you can see, this depends on Q1. So Q1 is the position of the first joint. dQ1 is the first derivative, so that's the speed of the first joint, and ddQ1 is the second derivative or the acceleration of the first joint. Okay, these are the inputs, and based on just this, right, we can generate a data set that we can use to train a neural network, and we can hopefully use a neural network to encode this massive equation. Again, this is one. There are 6 of them. Encode them into a neural network to simplify the process. Now, this is again purely mathematical, purely for show. Let's call it that. Purely mathematical, but we have equations that we know that we work, verify them, and we can actually. This is the scores. One is the best possible. You can see that it's very close, so it's not perfect, right? There is an error, but the reality is you don't need to be so precise, right? Because you're just calculating the needed power. If you're trying to design a robot, or you want to adjust something or optimize it, you don't need to have like a perfect model. You don't need to have a perfect prediction. Here the errors, it's in worst case, it's less than 1% of an error. compared to using that equation. So that's pretty good. That's very good. And this, when you're calculating it, when you're running the Python calculation or something, using this neural network that we developed is about 15 to 20 times faster than using that code to calculate. So we're talking about seconds versus minutes, right? In comparison to like the classical method. So the goal was simply to encode these extreme large equations, to simply encode them into the data set, and encode them into the neural network. So this is an example, and the final example we have of a more realistic usage is based on these two. We have the prediction of motor power or energy use of the robot. I'm going to share this, and this also has a data set that I'm going to, you can actually find it at the end. I'm going to show you where, just so you know, in the future, if you're looking at different data sets. What is the goal here? Well, the goal is to predict how much power the engine uses based on a certain position it's in, the moment, the speed it has. Why? Because then we can use that to optimize the engines and so on, to optimize the paths and of the robots, etc. Why is this interesting? Well, there are a couple of techniques here that I wanted to show you. First, the data is collected on a real robot, right? So it's realistic data. Here is the examples, the code, and everything. This is the variables that were used and how it was collected through the software that we used. Okay, so all of this mostly use multi-layer perceptrons or similar neural networks, which is why I'm not individually mentioning. Most of them use this cross-validation that I talked about. So what are the results here? There is another feature here that was used, and that's called dataset pruning. What is dataset pruning? Well, using certain techniques, such as a random forest, let me find it here. In correlation analysis, we can determine feature importance. So of these features that we have here, some of them may not be as important as we initially believed them. We may conclude that, hey, this element maybe isn't important, this maybe isn't important, but instead of talking and discussing it, we can actually observe the data. And when we observe the data, let me just go down here, we can see the feature importances with different techniques. And we can see that certain variables here have very, very little influence on the output. This means that these variables can be removed. Why is this useful to us? This is useful to us because we can use this to essentially prune the dataset, eliminate values, and create a simpler model, right? So as opposed to a mathematical model where we would need to use everything like this, we can just not use this in training. And usually this means that when we are comparing the pruned and the complete data set, we can see that the pruned data set will usually have a better score. Why does it have a better score? Because it's easier to regress, you have less variables. You can imagine it as having, are you putting together a puzzle with 100 pieces or 50 pieces? You would be much faster with less pieces. The same is with variables. We can see that on average, we have an improvement of a significant value. And even if you're looking at the minimal value of the pruned data set, it's better than the maximal value of the completed data set. So that's something that we can do. We can eliminate values in the data set to make the data set more easier to model. So yeah, this is the same, again, graphical comparison. It's not that massive of a difference, right? But the difference definitely does exist. Another benefit to this is something that I wanted to show you is that this was then tested using different robots, and this is something we also call synthetic simulation data. So when we're talking about synthetic data, right, as I mentioned, you can get it like mathematical simulation data where you're generating something mathematically, right, just calculating something. You have something that's synthetic data from a software simulation, or you have synthetic data that you generated using specific techniques such as generative adversarial networks. These are the different types of synthetic data. So when you see the term synthetic data being used or thrown around, someone is using it on you, you want to ask what's happening. And again, this was used. This is a bit of a different example. Instead of using synthetic data here to to improve the scores or something, we actually just used it to test the performance on different robots, right? So the model that we created works well for so we have this IRB 120 in the laboratory. We can see it has this score R2 should be high. This MAPE score should be low. That's an error. This is similarity, right? You can look at them this way. You can see that when you go to simulation, there's a drop because the real, the robot in the laboratory, there's some dust on it. Maybe it's not well oiled. Maybe it's not perfectly level on the position, and there are some influences there. That differentiate that a real robot. With the simulated robot that you can simulate. So that's something that I wanted to show you, that when you have a model developed in real data, you try to use it in simulation. There's a difference because yes, there is always a difference between the real data and the simulation. And as you go with different robots, we can see that this R squared drops and the MAPE increases because these robots, this robot isn't very similar to this one that we started with, right? So that's something. Another thing that I wanted to mention to you, to show to you, is essentially, where to find if you see something like this, a paper like this, and it says like, okay, this is interesting. I could use this for maybe a seminar or some research that I'm doing, or my final paper, something like that. Where can I find the data? So most papers today, this varies by publisher and so on. Something that's published in Elsevier might not require this, but Springer or MDPI may. So you will want to find something like this. It might be called different. Search for data, look at it, and it's called something data availability statement. And this data availability statement, will tell you like the original data presented in the study are made available or not. There are a couple of different elements here. Availability statement. Let me just find them. So this again, it differentiates. There's different elements that you can put here, or different publishers will require different things here. But if you see a paper that you're interested in, you want to check the data because you want to use it, or you just want to check it or something, first thing you want to do, use it to maybe expand on this. Maybe you see my results here and say like, oh, I can definitely do better, right? I can definitely improve this error and get a lower error. You can go, you can find my data here, right? Or other researchers' data, and click it. And it will lead you to a data set that you can download and use, right? For your research, etc. It will tell you what license it has. Please check. Again, this data set, I haven't added a lot of information to it, but usually, here I would need to add that, I would require you to cite something, a brief description of the data set. Another thing that you want to check is the license. Essentially, the license will tell you if you can use the dataset or not, right? Because the last thing you want is to, if you're a scientist, to write a paper, go to publish it, and then realize that you can publish that research because the paper, right, that you used here simply wasn't released under the license that says that you can use it for scientific research and so on. This essentially means that, you know, permissions hereby granted is free of charge to any person who obtains a copy of this software or documentation. To, you know, you can use it without restriction, without limitation, and so on. That's MIT license. Is pretty famous too, and it basically means you can do whatever you want with this data. Just give us credit at the end, and make sure that whatever you do is also released under the same license, right? So don't develop like a software that you're going to sell using the data that I've given you freely, you know. So what are some different data statements that you can have here if you're trying to get the data? You know, you should start with the paper and then go on. I will use, this is one of the publishers online, MDPI. Different publishers may have different suggestions on what to use in their data availability statements, but I think this covers a lot of different cases. So first, you know, and this is essentially, this is what is the status, what is the actual situation with data, and this is the statement that's going to happen. So for example, if data is available in the publicly accessible repository, you will need to share it, right? If another option that can happen is that the data is available or request because there are some restrictions. So for example, as I said, maybe due to GDPR or something like that, we talk about regulations, I'm not allowed to share this data outside of European Union or something like that, or I'm not allowed to share the data to anyone without the proper license and so on. So that's something that, you know, you may encounter. The data is available on request. A lot of people who don't like the idea of sharing their data will use this with anyone, right? Will use this. So if you get this statement, feel free to email the corresponding author, you know, of the paper. Oops, I made a mistake. Basically, if we go up here, you will see that one of the authors is going to have, at least one of the authors is going to have something like this email address here. It's going to be noted with something like a star, right? So for example, here, my colleague Angelic has a star here. That means that he's the corresponding author, and you can click here, get his email, and just send him an email asking like, hey, would it be possible to get the data for my project? Then we have some other examples. We have third-party data, where again some restrictions maybe apply. We will note where they were applied. So maybe it was, for example, that paper that I showed you in the start with the data that was collected on that LNG tanker. That was third-party data that was provided by someone, and it's available with the permission or not. Some data that is used in commercially might have an embargo placed on it, so you can't access it. Some other restrictions may apply to the dataset again, due to sharing, or maybe, you know, people who we were collecting the data from agreed to let us use it, but they don't want their public data to be publicly available. This is another interesting case where you have data available in multiple repositories and you're combining it, right, yourself. So you're creating a new data set, but you aren't generating any new data. Okay, all the data already exists publicly. Someone has collected it too, but you're aggregating it because you want to cross-reference something or analyze something. That data is that's something that was derived from the public domain, and is something that you can note as a separate data set that you can upload, but you also want to list where you got it. Data sharing is, again, if you don't have any data, some papers are just purely theoretical, they don't deal with data science and so on. Sometimes there isn't a lot of data, so you can just include it as a table. As I mentioned, if you have like 100 data points, few variables, you can just put it in the appendix to share that way. And finally, if you really don't want to share the data, but the editor isn't letting you, get away with telling that it's not available or so, you will have, again, something like this, that the data set is available on request. So it's not, difference here is essentially I have a reason that I'm going to state, so maybe privacy of my patients or ethical, legal reasons. I wasn't given the permission to share the data publicly. I was only given permission to use it, or I can share it outside of my country and so on. And this just means like I don't like sharing my data. I don't want to share my data right now. Maybe I'm planning to do some other research with it soon or something like that, and I don't want to publish it before I've exhausted all the research possibilities with this. So those are some examples of data. The last thing that I wanted to show you is just some data repositories where you can go and search for data in case you need it, right? So as I said, vast amounts of data, you can collect the data yourself. A lot of research today is done by using someone else's data. Why? When we're getting the data, data collection can be time intensive, it can be expensive, you may not have the equipment to properly collect the data, and so on. When someone else collects the data, if you're collecting it from a wider, they maybe have access to equipment you don't have. They may be, it's much faster to just download a data set than to actually measure it yourself. And that's fine as long as you give credit and it's, released under a proper, under a proper license that you can actually use. Here's my data set I shared before. Again, you have a different license here. So for example, this data set tells you that you can share, you can adapt it, but under the contribution that you need to give me appropriate credit as I requested in the data set. So that's something that you want to pay attention to. Okay, so let me just share a couple of these repositories for data that I personally find useful if you ever need any if you need to find information and so on. I'm going to share some of the places where I believe could be useful to you. So first of all, Kaggle. Kaggle is a bit of a mixed bag. Why? Because everyone can publish a dataset on it. It doesn't have any standard, any request. So there's a lot of varied datasets, right? There's a lot of information on different datasets, wine datasets, consumer price index, and so on. The problem with it is that anyone can publish the data, right? So you need to be very, very careful whether, when you're checking this, what is the source of the data, where it was given, is there any additional information on where it was collected, who published it, and so on. Please be careful if you're using something like this because, well, it's not curated and anyone can post any data that may or may not be valid. Usually try to make sure that any data that you have is referenced properly. It has like a paper behind it or an explanation of how it was collected. The best thing to do is to have a paper because then you can you can check the entire methodology and you can see whether it's fine, it's not fine, and it was already peer reviewed, so it was checked by someone who is an expert in the field before, multiple people who are experts in the field, to make sure that everything is fine. Okay, so another example where you may find it's Google Public Data Search. So what is the benefits? What are the issues with Google Public Data? If you're searching for something, it's going to find you a lot of information, but this isn't necessarily curated. You can see that this is just a Google search. You don't know what are you going to get. Oh, it's actually it has a new so it has this data commons. It's just a newer version of it. So if you search something, you can see it's not the best functioning out of all of them. So let's try something like car. It currently doesn't even work, but essentially what it did when it worked, it essentially Google searched trying to filter data. Let's see if we click on a certain elements, is going to allow you to explore data and so on. Again, it's like a Google search, so the same reason it's Google isn't perfect. It can be problematic to this data, how it was collected. It's not entirely clear. There's some AI in the background that's operating, that's trying to understand the elements here and so on. So be careful if you're using data like this, but it can be useful to find data. One of my referred data sets, let me just find it, is UCI machine learning repository. That's University of Irvine. This is created, when you contribute to data set, it gets checked. It's not as deeply checked, as some, but there is, some checking that goes on in the data. You can, the benefit of this particular website is that if you're searching, you can search for different types of data. So if you, for example, get a task that you need to do classification, you can search for classification. It tells you immediately the number of instances, the number of features that you have, and you can, very easily download and search the data here. And it offers you a lot of, nice tools, like you can directly import stuff in Python from the library. You can download the raw data. As I mentioned, you want to cite the data, you can automatically cite it from here in different styles, right? So that's very, very useful. It tells you who created the data. Each data set gets this DOI, which is a document identifier, which allows you to identify that data uniquely. And again, it has a license that you can check to see whether it's fine to use or not fine to use. This is my preferred location for datasets, data gathering. These days, I usually get data collected for me by other experts, as I showed you examples, where someone will collect the data and I will use the data. I don't really use public data that much unless I really run into something interesting or I want to do like a pre-check for the research. But mostly for my students, if I'm giving them tasks, I'm going to look for the data here or tell them to look here. Alternative to this is IEEE Dataport, which is very similar. It has a lot of information and so on, a lot of data sets. The problem with this is that you need to be, some of these are free to access, some of them you need to be logged in, and you need to have an account to access it. Unlike UCI, some of them are free. For some of them, you need to be a IEEE member, which will set you back like 10 euros a year or something like that if you're a student. So it's not the end of the world, but yes, but it requires some money, which might not be very practical for all of us. The benefit of IEEE Dataport is that all the papers all the data sets that are published here have a research article that's connected to them here, and you can check and you can make sure that the data is fine and that it was peer-reviewed and so on. So that's a big benefit of IEEE Dataport. So yeah, so those four are essentially well, these two mostly are where I look for data sets to find the data if I want to use publicly available data. Okay, so that's more or less what I had planned for today. From my side, again, if you have any questions or you want to share any information, if you like were you know inspired to talk about maybe some data collection that you've done or that you may need to do in the future, want to discuss it, or you just have some questions about what I asked, I'm going to give you like a minute or so now to raise your hand, start talking, type whatever is the easiest for you. So. Okay, I assume no one is really volunteering. So yeah, that's generally that's fine. Again, we have some time remaining because I wanted to make sure that if people, I see someone is typing. So while the people are typing here, I'm going to just write down my email address once more. In case after the class, you have some questions or something regarding, any of these papers that I posted or some of my other papers or just questions in general, feel free to ask me there. It's not a problem. I'm very open to communicating. Unless I saw some people were typing, they stopped now. I don't know if so I'm going to just riff on a bit in case someone posts something. But yes, in general, I hope you found the class more or less interesting. As I mentioned, let me say it again, you don't have that final paper or something. As I said, it's uh, today's that's exactly what. Thank you for the question. So now when it comes to this class, you don't have any obligations anymore. We were planning on giving you like a short paper to write, but again, it's 2 days until the end of the course, so we won't give you anything. With this class, you are done. You don't need to do anything. Now, for the other classes, for the whole course, right? Like Erasmus WICT course, it depends from class to class, but people who are holding the classes may have informed you of that. I know that I had a seminar for social aspects of AI, and I know that Introduction to HPC has a short seminar. I am not sure about the other classes. So if you are unsure, just contact the people whose class you're enrolled in. If you are unsure how to contact them, if you haven't attended classes or something, just message like that official email that we contacted you with information, and we will put you in touch with them. Other than that, Friday, I'm going to send you the data regarding the that you will need to fill out, and then we will, over the course of like next week or two, please keep in mind, it's Christmas and holidays in general, so it's going to maybe be a bit slower. We're going to start filling out these certificates and stuff for you. You will need to fill out a form with a bit of, some questions about the class and everything. And once you submit that, we will, create these certificates for you and send them to you via email. So look out for that at the end of the this week, probably Friday. Okay. Other than that, let me just wrap this class up. So when it comes to practical data collection, I hope I provided you some information on how to track the data, how to analyze it, and so on. So if you're ever collecting the data, you have to collect your own data in the future. I hope you will follow it. If you need public data, I tried to talk about that a bit. So hopefully that helps you. And again, if you have any questions or anything, feel free to email me, and that's it for today. If you haven't managed to ask a question here, or you have anything additional that you remember afterwards, just write me to my email that I posted here, and that's it. So thank you very much for your attention in these classes, and thank you for participating in the course in general. So thank you, and goodbye.
Thank you. Goodbye.
Thank you. Goodbye.
Thank you. Bye.
Thank you. Bye.
Thank you.